Right, 33%. Right. Right. So good morning, students. We can start. So where we stop? Wait, I will open my PowerPoint presentation. Right. Can you able to see the presentation? Karthik?
Yes, sir. It is visible.
Yes, right. So we are discussing about the basic thermodynamics, and let me know the basic terms used in thermodynamics today's class. So as I said early, what is a thermodynamic equilibrium? So if you can say the system is in a thermal equilibrium, mechanical equilibrium, and chemical equilibrium, then we can say that the system is in thermodynamic equilibrium. So first, let me know what is a thermal equilibrium. So thermal equilibrium, say for example, when a hot cup of coffee is kept in the room, heat flows from coffee to the surrounding air, right? So if you are having a coffee in a cup in the room, the heat flows from coffee to the surrounding air. After some times, the coffee reaches the same temperature as the surrounding air, and there will be no heat flow from coffee to air or air to coffee, right? So if we keep the coffee for a certain time, there will be no heat transfer because the temperature at the coffee also will reach the temperature at the surrounding air, right? So it implies that the coffee and surrounding air are in thermal equilibrium with each other. So this way we can call that the system is in thermal equilibrium, right? The system are said to be in thermal equilibrium with each other if they are at the same temperature. So this is which will not change with the time. So with the time there is no change in temperature, means we can say that system is in thermal equilibrium. Then mechanical equilibrium. So this is an example for mechanical equilibrium. So just consider the piston cylinder arrangement. So inside this piston, we filled a gas. So we can move this piston in the upward and downward motions. So consider a gas container with the piston as shown in the figure. When some mass is placed on the piston, it will move downward due to downward gravitational force. Say for example, if we add some mass, say for example 5 kg. So if we add a 5 kg mass in the over of the piston, we can get a downward motion because of gravitational force. And after certain humps and jumps, the piston will comes to rest at the new position. So after adding 5 kg weight, so it will come down and it will get some stable position, right? When the downward gravitational force given by the piston is balanced by the upward force exerted by the gas. Why it happens? Because of the upward force exerted by the gas. The system is said to be in mechanical equilibrium. So there will be a equilibrium in forces. There will be a equilibrium in forces. We are giving the downward force due to gravitational force. Then the upward force is exerted by the gas to balance this downward force. So after some times the system will be in equilibrium, then we can call this as an mechanical equilibrium, right? A system is said to be in mechanical equilibrium if no unbalanced force acts on the thermodynamic system or on the surrounding by thermodynamic system, right? So we can understand that what is mechanical equilibrium in the sense a system is said to be a mechanical equilibrium if no unbalanced force acts, right? If no unbalanced force acts on the thermodynamic system, we can call this system as an mechanical under mechanical equilibrium. So we know what is thermal equilibrium, then we know what is mechanical equilibrium, then next one is chemical equilibrium. So if there is no net chemical reaction between two thermodynamic system in contact, right? So when in contact there is a two system, if there is no chemical reactions happens, then we can call this system as an chemical equilibrium, right? So if there is no net chemical reaction between two thermodynamic systems in contact with each other, then it is said to be in chemical equilibrium, right? So we know what is thermal equilibrium, then what is mechanical equilibrium, and what is chemical equilibrium, right? So this is the main point. So why we learn these three equilibriums? To understand what is thermodynamic equilibrium. So if two systems are said to be in thermodynamic equilibrium, then the systems are at thermal, mechanical and chemical equilibrium with each other. So if you want a system to be in thermodynamic equilibrium, the system must be in thermal equilibrium condition, must be in mechanical equilibrium condition, also must be in chemical equilibrium condition. So in the state of thermodynamic equilibrium, the macroscopic variables. So we know what are all the variables in thermodynamics, such as pressure, volume, and temperature. Right. So these variables, pressure, temperature, and volume, will have fixed value and do not change with time. So for an instant time, we can say if a system is in thermodynamic equilibrium, there is no change in variables. There is no change in variables with the changing time, right? So this is the explanation about thermodynamic equilibrium. So if you want a system to be in thermodynamic equilibrium, that should be satisfy all these three equilibriums. So let's say chemical equilibrium, mechanical equilibrium, and thermal equilibrium, right? So this is a basic concept about thermodynamic equilibrium. Then we can move to the next slide. Next important term used in thermodynamics, state variables. So state properties. So in thermodynamics, the state of thermodynamic system is represented by a set of variables called thermodynamics variables. So we can also say state, or we can also the state can be determined by the thermodynamic variables. So if at any state, in the last class I said a point function, or we can say the state. A point, any point can be say as a state. So this state, each and every state will have its own variables. Examples: pressure, temperature, volume, and internal energy, etc. So these are some variables, thermodynamics variables. So this can be called as an state variables, thermodynamics state variables. So pressure, temperature, volume, internal energy, and so on, etc. can be called as an thermodynamic state variables. So these are the variables in thermodynamic states. Then the value of these variables completely describe the equilibrium state of a thermodynamic system. So if a system is in thermodynamic equilibrium, how can we identify? By using these variables, by identifying these variables, right? So heat and work are not. So we discuss about what is heat and what is work, and what both together. So heat and work are not state variables, rather they are process variable. So these pressure, temperature, volumes, internal energy, mass, density, specific capacity, specific heat capacity. These can be called as an thermodynamic state variables. Neither heat and work are process variable, right? These are all state variable. This heat and work are all process variables. So there are two types of thermodynamics variables. So we have two types. One is extensive and another one is intensive. So we have extensive variables. Also we have intensive variables. So how can we define? So extensive variables depends on the size or mass of the system. So if a variable, if a property, it depends on the size or mass of the system, we can say that is an extensive variable. Right. In simply, example for extensive variables, volumes, then total mass, entropy, internal energy, heat capacities, etc. So assume this volume. So extensive variables is a mass dependent, right? So extensive variable where mass dependent. How can we assume that? Take this volume. So if your system has volume V, right? Assume if your system has a volume V, if extensive variables in the sense mass dependent. So if you cut the system by two, if you cut the system by two parts, so part one will be half of the volume and another part 2 will be having the another half of the volume. So there will be a change in volume if you cut the system by 2, right? So if that happens, depends on the size or mass of the system, that can be called as an extensive variables. If there is independent with the mass, if the system is an independent with the mass, then the property can be called as an intensive variables. Right. The explanation is about intensive variable do not depend on the size or mass of the systems. Right. So example, temperature, pressure, specific heat capacity, densities, etc. Say so like that in the previous examples. So can we take a system with a temperature T? So if the same system is splitted by two half, right? In the system, first half system there will be a same temperature. The second half also there will be a same temperature, right? So assume a solid bar with a 40 degrees Celsius. So we have a solid bar with a 40 degrees Celsius. So intensive variable means independent with the mass. So if we are splitting that bar with the two half, if we measure the temperature at piece 1 and temperature at piece 2 will be same, right? So this is called the independent of mass, independent with the mass. So we can call this property temperature as an intensive property. In other case, in extensive property, so if we measure the volume of the piece 1 and volume of the piece 2, it was different, right? So piece 1 will be half of the volume and piece 2 will be half of the volume. So there was an dependent of mass. So this property can be called as an extensive variables. Then independent with the mass properties can be called as an intensive variables. So intensive, independent with the mass. Extensive, dependent with the mass. Just to keep in mind that. Examples for extensive, intensive properties: temperature, pressure, specific heat capacity, density. Right. So if you split the system into two half or into any other portions, there is no change. The property will be same as like in the whole system. Right. So that can be intensive variables. So if the properties were splitted accordingly with the properties of mass, that can be called as an extensive variable, right? So these are some basics. Then equation of state, right? The equation which connects the state variables in a specific manner called the equation of state. So we know what are the variables, what are the state variables. So these state variables are connected with a specific manner called the equation of state, right? Each and every state, as I said earlier, each and every state has its own variables. So these variables can be connected by some equation. So this equation is called as an equation of state. A thermodynamic equilibrium is completely specified by these state variables by the equation of state, right? Also in thermodynamic equilibrium, we can correlate these variables with the equation of state. If the system is not in thermodynamic equilibrium, then this equation cannot specify the state of the system, right? So if the system is in thermodynamic equilibrium, that should follow the equation of state, right? An ideal gas obeys, PV is equal to NKT. Here, K is a Boltzmann constant, N is a number of molecules, right? So also we can redraw this equation. PV is equal to NKT as PV is equal to mu RT. So mu is mole, R is a universal gas constant. Also we can have PV is equal to nRT. Here R is an characteristic gas constant. So we have various universal gas equation, but the general equation is PV is equal to NKT. Here P is pressure, V is volume, N is an number of molecules, K is in Boltzmann constant, then T is an temperature, right? So this is the universal gas constant. Right? For an ideal gas, this is an universal gas equation, thermodynamic equilibrium. Since all four macroscopic variables is pressure, volume, temperature, and N are connected by this equation, we cannot change one variables alone, right? So this is called the equation of state. For example, if we push the piston of the gas container, the volume of the gas will decrease, right? So if we push the piston, the volume of what will happen? The air inside the cylinder will get compressed. So the volume of the gas will decrease, but pressure will increase, right? So we discussed in early classes. So the volume will decrease, pressure will increase. Or if heat is applied to the gas, assume if heat is applied to the gas, its temperature will increase. The pressure and volume of the gas may also increase. So heat is applied to the air, the pressure will get increased. Also volume also will get increased. So this is the equation. So each and every properties, each and every state variables has connected with this equation that is called the equation of state, right? There is another example of equation of state called the van der Waals equation. So you have studied the van der Waals equation in physics. Then the real gases obey this equation of thermodynamic equilibrium. So we will discuss the gases, ideal gases in thermodynamics. So you have to know what is van der Waals equation. So what are the state of equation of state, right? The air molecules in the room truly obey van der Waals equation of state, but at room temperature with a low density, we can approximate it into an ideal gas, right? So the air inside the room also will obey the van der Waals equation or equation of state of an ideal gas, right? So just know that what is the equation of state. So for an ideal gas, the equation of state is PV is equal to NKT. So each and every state that has its own equation of state. Then the term internal energy. What is internal energy? So internal energy of a thermodynamic system is the sum of kinetic, potential, energies of all the molecules of the system with respect to the center of the mass of the system. So we are dealing about the gas. So the internal energy or say energy can be of a thermodynamic system is sum of kinetic and potential energy. The kinetic energy and potential energy comes together to give you an internal energy of a system. The internal energy due to molecular motion including translational, rotational and vibrational motion is called an internal kinetic energy. So how can we calculate the kinetic energy? Because of the translational, rotational and vibrational motion, we can get the internal kinetic energy. And how can we get the internal potential energy? The energy due to molecular interaction is called the internal potential energy. As we know, the molecules inside the gas will try to impinge the walls of the cylinder, walls of the system, right? So due to that impinging, there will be an internal potential energy. Due to the translational, rotational and vibrational motion of the molecules, there will be a kinetic energy. So both together will give you the internal energy. Say internal energy U is equal to EK, that is potential kinetic energy plus EP, potential energy. K in the sense kinetic, P in the sense potential, E in the sense in the energy or internal energy, right? So U is called as an internal energy, right? So since ideal gas molecules are assumed to have no interaction with each other, the internal energy consists of only kinetic energy part, right? For an ideal gas molecule. So ideal gas has its own molecules. These molecules are assumed to have no interaction with each other, right? So in an ideal gas, we are assuming there is no interaction with the molecules. So because of that, so the kinetic energy EK will be 0. Only the EP, potential energy. So molecular interaction is assumed 0 in the case of ideal gas. So the internal energy is purely dependent on the kinetic energy. Temperature, the number of particles and is independent of volume. However, this is not true for real gases like water vapor gases. So this this condition is only for ideal gases, but in the real gases we can't consider this one, right? Then internal energy is a state variable, right? Internal energy is a state variable. Note this point. Internal energy is a state variable. So we know what is state variables, right? It depends only on the initial and final state of the thermodynamic system. So internal energy can be calculated at the initial position, also can be calculated at the final position, and these two will differ from the states, right? So internal energy will differ with the position of the state. For example, if the temperature of water is raised from 30 degrees Celsius to 40 degrees Celsius, right? Either by heating or by stirring. So assume this one as an example. So you have water. So we want to increase temperature from 30 degrees Celsius to 40 degrees Celsius. How can we increase? By heating or by stirring, right? The final internal energy depends only the final temperature 40 degrees Celsius and cannot the way it is arrived at, right? So the before then the internal energy at 30 degrees Celsius and the internal energy at 40 degrees Celsius won't be same. So it can be calculated based on the temperature, not by the path traveled, right? So this is a term, internal energy in thermodynamics, just like that, just keeping that. So internal energy will be based on kinetic energy as well as potential energy. Then you have to know the term quasi-static process. So In blind, we can say quasi-static process is a dead slow process, right? Dead slow process, very slow process, right? So let me know what is quasi-static process. So consider a system of an ideal gas kept in a cylinder of volume V and pressure P and temperature T, right? So in a piston cylinder arrangement, we have the gas with some properties or some variables. When the piston attached to the cylinder moves outward, the volume of the gas will change, right? So if we move the piston outward, there will be a increase in volume, right? As a result, the temperature and pressure will also change because all these variables P, T, and V are related by the equation of state PV is equal to NKT, right? So if we change the volume, there will be a change in pressure, there will be a change in temperature. So these three variables are linked together with this equation of state PV is equal to NKT. If a block of some mass is kept on piston, it will suddenly push the pistons downward. So if suddenly we place a weight over the piston, it will suddenly push the piston downwards. The pressure near the piston will be larger than the other parts of the system, right? Immediate portion of the piston. The immediate portion of the piston has higher pressure, but in all other positions there will be a changes in pressure at certain instant. Uh, at certain instant, this will happen. So the immediate portion of the piston has more pressure compared with the all other position. It implies that the gas is not equilibrium state. So you know what is equilibrium state? So equilibrium state is an uh, zero reaction, right? So we can't say this sudden reaction is a non-equilibrium state. So we cannot determine pressure, temperature, or internal energy of the system until it reaches another equilibrium state. You know what is equilibrium? So there is no forces reactions happens. If there is no thermal reactions happen, if there is no chemical reactions happening, then only we can say that the system is in equilibrium condition. So for a certain time, for a certain instant, we can't say the system is in equilibrium condition. So we can't determine pressure, temperature, and internal energy of the system until it reaches another equilibrium state. So after sometimes it will come to equilibrium condition. So if we leave the system for a certain time, say for example, it may be a minimum time. So if you leave the system for a certain time, then it will come to the equilibrium position. Right. But if the piston is pushed very slowly, such that at every stage it is still in equilibrium with the surroundings. So assume this the process was dead slow. So if you add weight immediately to the system, it is non-equilibrium state, right? If you add a small mass, say for example a minute mass or infinitesimal mass, so that can be give you the system as an equilibrium state. We will see the example the next slide. So we can use the equation of state to calculate the internal energy, pressure, and temperature. So in this equilibrium condition, so this kind of process is called a quasi-static process. So you know what is the impact? You know what is impact? So impact is a sudden force applied to the system, right? So like assume like that. So non-equilibrium state is an immediate transfer of the forces. Equilibrium state is a dead slow process. So this process is a quasi-static process, right? So definition is a quasi-static process is an infinitely slow process in which the system changes its variables so slowly such that it remains in thermal, mechanical, chemical equilibrium with its surrounding throughout. Right. So if your process is in quasi-static process, this condition should be satisfied. By this infinite slow variation, the system is always almost close to equilibrium state. So we can say in a quasi-static process, the system in all the time can be said as the system is in equilibrium state. So the equilibrium state and quasi-static process are linked together. So if you want a system, if you want a process is in quasi-static, the system at each and every point should be under equilibrium condition, right? So this is an example for a quasi-static process. So consider a container of gas with a volume V, a pressure P, and temperature T. If we add a sand particle, so this is a quasi-static process. So sand particles won't change the properties suddenly, right? If we add the sand particles one by one slowly on the top of the piston will move inward very slowly, right? Note the point, very slowly. So this is quasi-static process. This can be taken as almost a quasi-static process. Right, this is an example of a quasi-static process. So quasi-static process is an infinitely slow process under the thermodynamic equilibrium of the system. Right. Then the next term you want to know, PV diagram. What is PV diagram? So in the last class itself we discussed what is PV diagram. So each and every thermodynamic processes has its own PV diagram. So let me know what is PV diagram. So PV diagram is a graph between the pressure and the volume of the system. The PV diagram is used to calculate the amount of work done by the gas during expansion or on the gas during compression. Right, we can calculate the work done. How can we calculate the work done? By using PV diagram. So the area under the curve, the area under the PV diagram will give you the work done. So this portion. So this is a PV diagram. So P in x-axis and V in y-axis. This is pressure in pascals. This is uh, volume. So the PV diagram. This is a process. So this is one state Pi and Va. P initial and V initial is in one state, and P final and V final is in another state. P another state. This is state one state. This is another state. Then this path. This is the path function. The process is happened by this path. Right. So how can we calculate the work done? So by calculating this area under this curve. So this portion, this added portion will give you the work done. So work done is equal to area. By using a differentiation, we can get the work done. So here is pressure, and there is a change in volume. There is a change in volume. So pressure is a constant. By keeping pressure as constant and the change in volume, dV in the sense the change in volume. So dV changes from initial to final. dV changes from initial to final. We can take V outside. We can differentiate V by putting the initial and final values. Then we can calculate the work done by the system. So why we need PV diagram? So to calculate the work done, to understand what is the process, and to understand what are the states of variables, what are the states, what are the initial state, or what are the final state. So from the PV diagram we can identify, we can also get the variables at initial at each and every points and paths, how it travel. So we can get some more knowledge regarding the thermodynamic processes by knowing what is a PV diagram. So let me know PV diagram. The PV diagram is the graph between pressure and volume of the system. PV diagram is used to calculate the amount of work done by the gas during expansion. So you know what is expansion, and you know what is compression. So in both the cases, we can calculate the work done. Right? You know how to calculate the integration. So in mathematics, you may know how to calculate the integration. The area under the PV diagram will give you the work done during expansion and compression. Right. The shape of PV diagram depends on the nature of the thermodynamic process. How the shape of the PV diagram happens? How can we arrive this PV diagram? Because the nature of the process. You know, this expansion, isothermal expansion, we have isothermal compression, we have isochoric expansion, isochoric compression, isobaric expansion, isobaric compression. We know reversible adiabatic process, so like that. So this PV diagram is depends on the nature of the thermodynamic processes. So we have seen the isothermal, isochoric, isobaric processes in the last class. So this PV diagram is based on the thermodynamic processes. So this we discussed earlier. So we can move to the next slides. So this too can be calculated by using this PV diagram, right? Also work done. This work done is calculated. The area under the curve will give you the work done of the thermodynamic process. So we will look at that this PV diagram for all the processes one by one in the next class. So this is an state variable, temperature is a state variable, then pressure is another state variable, then heat and work are another process variables. Then we are looking what is a reversible process in the last class, right? We stopped here. What is reversible process? A reversible process is one where the infinitesimal change in the condition of the surroundings. Infinitesimal in the sense small changes. Right? Infinitesimal changes, small changes in the condition of the surroundings is a reversal of the process. We can say a quasi-static process. So infinitesimal change is also can be taken as a quasi-static process. So infinitesimal equal to quasi-static, right? Or small changes leads to reversal of the process. So we can also have some processes in reverse manner. That process is called as a reversible process. The system is very close to equilibrium, and infinitesimal changes can restore the system and surroundings to its original state. This is another explanation about the reversible process. Say this one. So take this diagram. This system has temperature T. This surroundings has temperature T minus there is a small changes. So the temperature is less compared with the system. The temperature of the surrounding has a lower temperature compared with the system. Then what will happen? There will be a heat flow in this direction. So there will be a heat flow from the system to the surrounding. What will happen if we heat the surrounding? If we heat is added to the surrounding, the temperature is more with the surrounding and temperature is less in the system. So the more heat is try to flow from surrounding to the system, right? So this is called as a reversible process. So if the process happens reversibly, then we can say the process is a reversible process. So this is an example for not reversible process. So if the temperature of the system is 40 degrees Celsius, the temperature of the surrounding is 80 degrees Celsius. So the heat we can't have this heat flow direction reversibly. So the heat flow will be from surrounding to the system, right? So this is a not reversible process. So what is reverse, right? So okay, this is another visualization of reversible equivalent to a irreversible process. Let us keep one example in mind as to how we can construct a reversible equipment to a irreversible process. Let us consider the example of the freezing of a undercooled water. So the term undercooled water. So undercooled implies that the water is held in the liquid state below the bulk freezing point. What is the freezing point at the temperature? So what is freezing point in the water? So that is 0 degrees Celsius or 273 Kelvin, right? So how it is possible? So this is undercooled, the term undercooled water. So we can have undercooled water as well as undercooled ice, right, at -5 degrees Celsius at 1 atmospheric pressure. The freezing of undercooled water is irreversible. This one. So in -5 degrees Celsius, we can have water. Also in -5 degrees Celsius, we can have the ice. So this process is irreversible. How? So this we can't change the state. We can't change the phase immediately. So how can we change the phases? So in this reaction, we see the P2. In these reactions, we can change its phases. So from water at -5 degrees Celsius, if you heat, we can have water at 0 degrees Celsius, -0 degrees Celsius. Then it will try to ice. It will try to crystallize. So ice at 0 degrees Celsius. Then we cool. If we cool, then we can have the ice at -5 degrees Celsius. So also we can reverse the process. So ice at -5 degrees Celsius. If you cool more, then it will comes to ice at 0 degrees Celsius. Then the ice at 0 degrees Celsius, if you heat, we can have the water at 0 degrees Celsius. Then if we heat again, the water at 5 degrees Celsius can happen. So this is a reversible process, but this phase is an not irreversible processes. So we can visualize this process as taking place in 3 reversible steps. So this is a reversible step, this is a reversible step, this is a reversible step, but this is not an reversible step. This is an irreversible step. Right, reversible PV work on a closed system. So you know what is PV diagram, and what is what is a reversible process, and you know what is closed system. Right. So what will happen in a reversible PV work on a closed system? In a closed system, say for example, piston in the example figure below. So this is a closed system. We have piston cylinder arrangement. This is a piston. This is a cylinder. Here we have pressure, the pressure of ideal gas. Also we have the temperature. Also we have the volumes. Right. The system is close to equilibrium during whole process, thus making the process reversibly. So if the process is in quasi-static, if the process of the system is quasi-static, you know what is quasi-static? It's slow process, right? So if the process is quasi-static, then we can get the process reversible. As change in velocity is negative, so if we compress, so pressure is applied. So pressure plus change in pressure is applied. So the change in volume. So from higher volume to lower volume. So change in volume is negative, while the work done is positive. So how can we calculate the work done? So by using this equation, change in work done equal to minus PdV. So you know the area under the PV diagram will give you the PV work done. So we can calculate the work done by using this formula dW reversible equal to minus PdV, so, or integral PdV. So here del V is negative and del P change in pressure is positive, and work done on the system is positive, work done by the system is negative. So the, note down this points: work done on the system and work done by the system. So work done on system in the sense we are applying the work to the system, so that will be positive, and work done by the system. So if you get some work by the system, by the system, we can say that work done by the system. So differentiate the two terms: work done on the system and work done by the system. So work done on the system in the sense, so we are doing work on system. Work done by the system in the sense the systems will do the work, right? Just compare these 2 points. So work done on the system is positive. So work done on the system is positive, and work done by the system is negative. Right? If the piston moves outward under influence, then the work done is negative. So uh, if you push the piston, the work done is positive. If we uh, move the piston outward, the work done is negative. So there will be a interrelation with the uh, work done on the system and work done by the system, also by the change in velocity, the change in volume. Right. Note that the pressure is the pressure inside the container. For the work to be done reversibly, the pressure outside has to be pressure more, plus P plus del P. Plus del P. The del P in the sense more temperature, right? Small change in pressure. Since the piston is moving in a direction opposite to the action of P, the work done by the surrounding is P del V. How can we calculate the work done? P del V. The work done by the system is minus PdV, a negative. Here we have negative because we are doing the work by the system. So the system is doing work, so we have a negative formula minus PdV. So we can reverse vice versa. So if the work done on the system, there will be a positive work done. If the work done by the system, there will be a negative. So this is done by the system. So ultimately, all form of energy will be converted to heat. We can convert all the form of energy to heat. So no need to understand these points. This is the reference of Keynes, the famous author Keynes, about the points of reversibility work on process system. So just skip this point. Then you know what is a reversible process. What is a PV diagram will give you the PV work. How can we calculate the work under the PV diagram? Then we discussed in the early classes what is the state function. So each and every state has its own properties. So that is called the state functions. Also, you know what is work done. Work done can be internal energy, higher internal energy, minus lower internal energy. How can we calculate the internal energy? The difference in the internal energy can be calculated as a work done. So also we have another definition for work done. So work done can be calculated. So change in internal energy. The change in internal energy can be said to be as an work done. So if higher internal energy is reduced to lower internal energy, then the change in internal energy will give you the work done. Right, the internal energy of an isolated system is constant. So you know what is isolated system. So for an isolated system, there is no change of mass as well as energy transfer. So there is the internal energy is constant. You know, so for an isolated system, we can't transfer mass neither energy. So the internal energy is constant. The process for which the final and initial states are same is called a cyclic process. So if how can we call this cyclic process? Cyclic process is a repeated one. So if the states can be differ, so final state and initial state may be differ, that is a process. If the final stage and initial stage is the same, that is called a cyclic process. So we can have the example in the next class or in the next slides. So yes, a process for which the final and the initial states are same is called a cyclic process. Right. So we can continue. What is cyclic process? So cyclic process, the initial state and final state will be same. This is a cyclic. So assume this one. So this point P, or this point C. From this point, we are processing this path. We are following this path to achieve this point. Then after another process happens to by this path, and at the final stage, the state is here. That is called cyclic process. You know, cyclic, the reverse. So initial and the final states are same means we can say that process is a cyclic process. For a cyclic process, change in state function is 0. So you know, change in state function. So there is no change in the pressure. P initial and P final will be same. The T initial and T final will be same. There is no change in state functions. Also, there is a delta U. Delta U in the sense internal energy is also 0. There is no change in internal energy for the cyclic process. Right. So this is an analogy. So take this analogy. A property which depends only on the current state of the system is called a state function. So this is the explanation about what is state function. The property which depends only on the current state of the system. So each and every state has its own properties. It has its own variables. So like temperature, pressure, volumes, like etc. So that is called a state function. This does not depend on the path used to reach the particular state. So we can have different paths. We can have different paths, but it won't depend on the path. So state functions won't depend on the path. So here we have analogy. One is climbing a hill. So assume this figure. Assume the figure in the below. So one is climbing a hill. The potential energy of the person is measured by the height of the center of gravity from ground level. So one is climbing by these two ways. So here we have path C1 and another path is C2 to get point P. So from ground level to point P, the person is climbing in two ways, two paths. If you calculate the potential energy, the potential energy for the both processes will be same. If a person is at H, the point P, then his potential energy will be mgh. How can we calculate? This is the formula. By using this formula, potential energy is equal to mgh, irrespective of the path used by the person to reach the height. Right. So we can have C2, C1 paths, but the potential energy for these two processes paths will be same. So this is called a state function. So state function is not dependent on path. This is an example of state functions. Then what is spontaneous process and what is a driven process. So spontaneous process is one which occurs naturally. So spontaneous, meaning of spontaneous. Spontaneous is a natural process. So example is downhill. So downhill in energy is an example of a spontaneous process. So the kind of energy downhill in energy is a kind of energy we are wait a minute. It's a kind of energy by calculating it gives a free energy. This is a basic physics, so you no need to bother about this. Just so spontaneous energy is an energy which occurs naturally. So seeing this figure, so a driven process is one which this is opposite. So spontaneous is there is no work involved, but a driven process is one which wherein an external agent takes the system uphill in energy, right? So in the next you can understand that. So in the next graphical representation, you can identify that spontaneous process. So this is a spontaneous process. How can we say this is a spontaneous process? So uphill, downhill energy. So if this ball is come from the top of the hill, that is called downhill energy. This downhill energy, again I am repeating, is downhill energy. So this downhill energy is a spontaneous process, where driven process is one which an external agent takes the system uphill. So if you want to take this ball to the uphill, how can we take? Say doing some external work, that is called a driven process. So usually by doing work on the system. So you have to do the work on the system. So this spontaneous work may be doing work by the system. Later on, we will note that the entropy. So the next term, the important term in the thermodynamics is entropy. We will discuss in detail in the next class. Later on, we will note that the entropy of the universe will increase during spontaneous change. So during spontaneous change only, there will be a change in entropy. Right. Entropy can be used as a single parameter for characterizing spontaneity. So this entropy and spontaneity is linked together. Just keep the terms entropy and spontaneity, spontaneous process in mind. We will discuss what is entropy and what is how the entropy is related with spontaneity in the next class. Then heat capacity we will discuss in the next class. Then go to the first law of thermodynamics. So we know we have four laws in thermodynamics. So sorry, zeroth law of thermodynamics. So we have four laws. One is zeroth law of thermodynamics. Then we have first law of thermodynamics. We have second law of thermodynamics. Then we have third law of thermodynamics. First, we can see what is zeroth law of thermodynamics. So here I have attached a video in video from Dixa. This you can visualize what is zeroth law of thermodynamics. When there was a video, I will play this. Play. Start playing. Wait, I will try to this web link. And wait a minute. Okay. Friends, can you able to hear me?
Yes, sir.
Yes, can you able to see the presentation of the page? Can you able to see the page, Diksha?
It is not clear, sir. Now we can't see.
Hello.
Yes, sir.
Page தெரியுதாமா?
Sir, in the attendance page, Google Meet and Teams
இல்ல,
ஓட பேஜ் தான் சார் தெரியுது.
இப்போ தெரியுதா திக்ஷா?
இப்போ தெரியுது சார். ஆனா கிளியரா இல்ல சார்.
இல்ல, வீடியோ இன்னும் கிளியர் ஆகல. வாய்ஸ் கேக்குதா மட்டும் இன்ஃபார்ம் பண்ணேன்.
கேக்குது சார்.
வீடியோல ப்ளே ஆகிற வாய்ஸ் கேக்குதாமா உங்களுக்கு?
வீடியோல ப்ளே ஆகுற வாய்ஸ் கேட்கல சார்.
இப்போ கேக்குதா?
இல்ல சார், வீடியோவோட வாய்ஸ் கேட்கவே இல்ல.
Yes, there was a video, audio attached with the video, but I will try. வீடியோ மட்டும் ப்ளே பண்ண பாருங்க. சப்போஸ் ஆடியோ கேட்கல அப்படின்னாக்க I will explain. So just what is zeroth law of thermodynamics? We have a video here, so I will play this video. Just to go through this video, I will explain what is zeroth law of thermodynamics. So there is a three systems. So we have system A, and we have system B, and we have system C. So these two systems A and B is in equilibrium, and A and C is in equilibrium, but B and C is not in equilibrium, in contact. So So look at this one. So the system A is in contact with the system C. The system B is in contact with the system C. But there is no contact with the systems A and B. So A is contacting with C. There is a contact between system A and system C, and there is a contact between the system B and system C, but there is no contact between the systems A and B. Because of thermal equilibrium, we can also have the thermal equilibrium with the systems A and B. So T refers temperature of system A, TB temperature of system B, then TC temperature of system C. So if there is a contact between A and B, A and C, and A and B and C, we can say the system A and B is in thermal equilibrium. So this is an example of a thermal equilibrium. So this is another example of this is another application of thermal zero of thermodynamics. So the temperature measurement by using the thermometer is an application of zeroth law of thermodynamics. So what is zeroth law of thermodynamics? If a system A and A and B in contact, A and C is in contact, but B and C is not in contact, means if we keep the system for a certain time, all these three will have equilibrium condition because of zeroth law of thermodynamics. Yes, you can play this video by your end, and you can understand what is zeroth law of thermodynamics. Sorry for the technical issue happens here. So you can play from your end. There was a link attached in your PowerPoint presentation. Yes, you can click that PowerPoint presentation. Also, you can refer this URL link to know what is zeroth law of thermodynamics. So Ma. Yes, சொல்றியாமா எனக்கு இன்னும் இப்ப கேட்கலாமா? 8 to 10 minutes zeroth law of thermodynamics explanation மட்டும் கொடுத்துட்டு ஸ்டாப் பண்ணிக்கலாம்.
சார்
சொல்லுமா.
சார் வீடியோவே தெரியல சார். அந்த வீடியோ இதுக்கு முன்னாடி ப்ளே பண்ண வீடியோவே எனக்கு தெரியல.
Yes, you can play your video link கொடுத்துட்டேன். வீடியோ கிளிக் பண்ணாக்க you can play. Video link கொடுத்ததுக்கு அப்புறமா just click பண்ணாக்க you can play that video. Let me know what is zeroth law of thermodynamics. I have another slide to explain zeroth law of thermodynamics. Yes. This is an exact explanation about the zeroth law of thermodynamics. When a body A is in thermal equilibrium with the body B and also separately with a body C. So A is in contact with the body B and separately contact with the body C, but there is no contact with the B and C. Then, but B and C will be in thermal equilibrium with each other because of this zeroth law of thermodynamics. This is known as zeroth law of thermodynamics. This is the basic of a temperature measurement. In order to obtain a quantitative measure of a temperature, the reference body is used and a certain physical characteristic of this body which changes with the temperature is selected The changes in the selected characteristics may be taken as an indication of the changes in temperature. So the thermometer is working this principle. So the selected characteristic is called the thermometric property. So on this reference body, which is used in the determination of a temperature, is called the thermometer. So a very common thermometer consists of a small amount of so this is the principle of a thermometer. So the thermometer is worked based on the zeroth law of thermodynamics. What is zeroth law of thermodynamics? So when a body A is in thermal equilibrium with the body B and also separately with body C, then B and C, the system B and C will be in thermal equilibrium. So this system B and C is not in contact, but this will gain thermal equilibrium under sometimes, after some time. So this is called as a zeroth law of thermodynamics. Just you can click that URL to play that video, then you can understand what is that. So the simple definition of zeroth law of thermodynamics is this one. It's three paragraph, it's 3 lines. Just you can go through that video and you can get some more idea about what is zeroth law of thermodynamics. Right, so we can stop here. We can discuss more about the thermodynamics in the next classes. So also I have attached videos, NPTEL videos in your files folders. So if you go to your files in MS Teams, there was attachments, attendance books thermodynamics, NPTEL IIT Madras thermodynamics. So go through that NPTEL IIT Madras thermodynamics videos one by one. So there was a serial numbers from 01, 02, 03, 04 to 65. So there we uploaded 65 videos in NPTEL from IIT Madras. We can get some more knowledge about what is thermodynamics by referring that videos. So if you have times, just play the videos one by one, then we can follow what is thermodynamics. So with this, we can conclude today's class. If you have any queries, you can ask now, or you can hang up your team. Thank you. Have a good day.
Thank you, sir.
Thank you, sir.
7.